recordings are now going on to YouTube because of something NAU did to me. Yeah. So links to YouTube, I can start, yeah, never mind. We want to, when we build these CMOS circuits, whether it's an inverter or an AND gate or whatever we're building, pretty much we're building them on those wafers like I showed you yesterday, those circular die. And if I can fit more circuits in that circular area, if I can fit more die in there, I can charge more. The manufacturer who makes those things is going to charge me a fixed cost per wafer no matter how big the die are. But if I can make the die smaller, I can cut them into smaller pieces and I can charge more customers. So I can get more money off of them. So I want the smallest circuits I can possibly design. Generally with digital circuits, almost always you're going to use the minimum length for the transistors. The reason why, and we'll go through this a little bit later, is if I increase the length, I'm actually going to decrease the performance of the device. Smaller L gives me better performance. Bigger W gives me better performance. But there's no gain by making L bigger unless I'm doing an analog circuit or I want a big driver. So almost always I use the minimum L. The L is so important to the process. When I talk about a 5 nanometer process, or we talk about the 180 nanometer process that we use in this course, that's the name of the process. And generally it's whatever that name is the minimum length of the transistors. The only thing I have as a circuit designer to change the performance of my transistors is adjusting W. So I can increase W to make the performance better. At the trade-off, I'm going to make the circuit bigger. I'm going to be able to fit fewer of them on that wafer. And so I'm going to have to charge more to make my money back. Now we're going to talk about a thing called noise margins, and I don't think we got to it a little bit in 280. If I have an inverter and I have the luxury of just driving the output of the inverter with another inverter that's sitting right next to it, I'm not going to have a lot of pickup. I'm not going to have a lot of noise on the line. Every time I make the line length longer, it's going to mean I have more capacitance on that line and more resistance, so I'm going to have a longer delay. But it's also going to be running parallel and close to other lines, and the signals that are on the other lines can feed through onto this line. And they create these little noise bumps. So it's not really perfect. This is what I drive out of here. By the time I get to the other side of the wire, I'm starting to see a bunch of little bumps on my signal. That's normal. We accept that generally with digital signals. So what I do, my output voltage is coming out at some typical voltage V out low. I'm seeing fluctuations around V out low, but this inverter here that's acting as an input is going to say everything below V in low is still a logic 0. So there's nothing on that line that's above V in low, so it's clearly always logic 0 as I intended. Now the problem happens when I come through here and I've got a big chip and I need to route the output of this inverter to something that's sitting far away. And I'm going to have to go through a few gyrations and go through some 90-degree angles, which tend to distort my signal also on that routing. And instead of having this nice smooth output that I put out from inverter 1, I have bigger fluctuations because of my routing on inverter 2. As long as those outputs are below V in low, I'm okay. Maybe right here, I might have a fault strip at a 1, But the way to improve this is, you know, I don't really have the luxury of controlling the routing. The routing's done by an auto router. It's going to do the best job it can, but it's going to do things like this. And just for someone to sit there and lay it out by hand would probably take years for what I can do in a couple of hours with an auto router. So if I want to make this better, one of the things I could do is increase the amount of voltage difference there is between V in low and V out low. And if I do that, then this is going to be more likely to pass and guarantee that I get a 0 all the way through. So the difference between V in low minus V out low is a very special parameter that I want to maximize as much as I can. And we call this the noise margin. And in this case, this is the low noise margin. It's the amount of crud I can get on my signal and still have a valid input. Now, this is what you're going to be measuring in lab 1. You're going to be doing a voltage transfer curve for an inverter. And the way Mentor Graphics does this, is you've done this before. It's like a DC sweep in Multisim, but we're going to do it in Mentor Graphics. This is my input voltage axis. And I'm going to vary my input voltage. I'm going to start out at an input voltage of 0, and the simulator is going to calculate what the output voltage is. And then it goes and it increases the input voltage ever so slightly and measures what the output voltage is. It does that over and over again and will generate this curve. Generally, you'll have more points in between there, so you get a smooth looking curve, but it's actually doing it discretely. Now, if I look at this, okay, my input voltage here is low, a 0, and I'm, sorry, I'm getting a 1 on the output. My input voltage here is high, it's a 1. I'm getting a low value on the output, so it's an inverter. Now, there's 2 places on here that we really tend to look at is the transition between when it's really acting digitally and it's not. And the way a lot of people define this is they look for a place on the curve. That's why I like Mentor, one of the reasons why I like Mentor so much better. They look for 2 places on the curve where the magnitude of this slope, or the slope of this line, is -1. And there's 2 places it passes through that. One, we're just going to eyeball it here, like we did in 280. Mentor's got a really nice tool where you can actually plot the derivative of the curve, and you can see where it passes through the -1 point. At this point, before this point, right here, this is digital. And it's a digital with the output low. This is the other digital state. It's also digital up here, and the output is high. In between those 2 lines is when you go into linear mode. This is where you're going to use the transistor as an analog circuit because it has a large slope. You can get a lot of gain out of it. But we don't want to use that region for digital. So this is analog. And they roughly correspond to the 3, well, they do correspond to the 3 regions of operation of a transistor. Yeah, one of them in this state, one of the transistors is going to be in triode, and one's going to be off, whether the PMOS or the NMOS. And in this one, the other transistor will be in triode, and then the other one will be in off. And in this one, they're both in saturation. Both the transistors are in saturation, and it's acting like an amplifier.
Julie, when you said this one and this one, I couldn't quite see where you were pointing.
Oh, yeah, because I'm, okay. So this is digital. And one of the, if you think about a CMOS inverter, you've got 2 transistors. In this region, your output's high, so this transistor is going to be on. You will be in triode. And this transistor will be off. And then this is when this is low and this is high. Now, if I switch that and I say the input's high, then this transistor would be in triode and this one would be off. Here's an E. This would be off. My output would be low. If I go somewhere in between the two, we need a third color. Like say I'm like half VDD over 2, or I'm just going to call this half. If I'm at, that's not enough contrast, I don't think. If I'm at half, then basically what happens is both the transistors are in saturation. And I'm in this part of the curve right here. Okay. So that's the idea. Now I need to define my VO high, my VO low, and all that stuff. And I can get that information off the voltage transfer curve. And this is what shows up on your Lab 1 quiz. And this is what you'll be doing on Lab 1. If you want to know what's in the Lab 1 quiz, I tell people this and they don't believe me. It is literally the instructor questions in the lab. And they don't believe me until after the second or third lab. So those are the things to study for that. Now I've got this voltage transfer curve that I've measured, and you will measure it in the lab using a simulator. And I go through and I plot, what I'll do is I'll plot another curve that is basically the derivative of this curve. And what I find is I find two places on here where the slope is the magnitude.
I only eat mac and cheese on Thanksgiving, and I pay a very huge price.
And this magnitude of the slope here is -1. Now the way these
Gabe, you're not muted.
The way these are defined is if I take the y coordinate at that point, I get, this is the output axis. So this is V out and it's high. And if I take the x coordinate of that point, sorry for the sloppy drawing, it actually looks better on the whiteboard. I get, this is the input axis, so this is Vn, and it's low, so that's Vn low. So the x and y coordinate at that point defines two of those parameters that I'm looking for. I get VO high and Vn low from that one point. If I find the x and y coordinate of the second point, I can get VO low and I can get Vn high. So once I get those four, I can calculate the noise margins. My noise margin low, I always get the polarity of this wrong. Surprise, surprise. Where is it? The noise margin's Vn low minus V out low. So the noise margin low is Vn low minus V out low. Generally, I calculate them. If it comes up negative, I just flip the sign. Is the way I always do it. The noise margin on the high side is also important. And in this case, it's going to be V out high minus V in high. So I get those, I measure those four numbers off the graph and I can get the noise margins. The other point on here, another thing I can get off of the graph is something called Vm. And Vm is the point where the input equals the output. So I just move my cursor on the graph over to where the x coordinate and the y coordinate are equal, and I get that midpoint value. Now for an ideal inverter, there's a whole bunch of different ones that you'll see, and there's some example ones in the lab. But for an ideal inverter, what I would really like to have to maximize the noise margins would be something that looks like this. My V out high equals VDD. My VN low equals my VN high. They both equal VDD over 2. Right in the middle. And my VO low equals 0 volts. This will give me the maximum noise margins. My noise margin high equals my noise margin low equals VDD over 2. This isn't quite there. To make this more ideal, I'd want to move this line closer to VDD. I'd want to make this slope steeper, and I'd want to move this closer to ground. But CMOS gives you about the best approximation of the ideal voltage transfer curve that we can get out of any logic family. That's one of the reasons I like it, other than the circuit's so simple. Okay, yeah, we just did that. So here's the big idea. And this thing again, huh? I've seen this in 280 a lot. If I can, this is a voltage divider. So what I want when the output is low is I want this resistance to be as small as it possibly can. And I want this resistance to be as big as it possibly can. And then my voltage will pull closer to 0. Approximately equals 0. Now, if I flip that around, and if my output is high, then I would want this resistor to be as big as I possibly can. I would want this one to be as small as I possibly can to pull my output up to high, as close to VDD, which is 1.8 in this case, as I possibly can. So ideally what I want is situations that look like this. I want these transistors to have very low on resistance, and I want them to have high off resistance to get these values as close to VDD as I possibly can. The only control you have as a circuit designer is how big is W, because L's useless. So we're going to do that. We're going to like look at these qualitatively and see what happens. Okay. I've got this voltage divider. And basically, we could model these as being the on, one of them's on, one of them's off, the on resistance and off resistance of the transistor. When a transistor is on and it's in digital mode, it's in triode. And you can dig this equation out of the book if you're extremely patient, because it's hard to find where they explicitly say it. But the RDS in triode basically equals the transconductance parameter of the transistor of the process. We don't have any control over that once we pick the process. Times W over L, V over voltage. So if I increase the W of the N-channel transistor, the resistance of that transistor is going to go down. Because I increase W, the number in the denominator gets bigger, RDS goes down. If RDS goes down, I make this on channel even smaller, my voltage divide, and this is fixed, this is going to get, just by the voltage divider rule, this is going to get closer to ground. V out low is going to go down, which is what we want for our noise margins. So WN going up is a really good thing to happen if we want to get better performance out of this device. Now, if Ln goes up, it's proportional to W over L. So an L in the bottom of the denominator of the fraction is going to cause the resistance to go up. If I increase this L, my Rn goes up. This, instead of getting smaller, gets to be bigger. I have a bigger resistance when it's on. V out low is going to go up. This is a bad thing. We never want to increase the L because it's going to affect our noise margins in a bad way. If I increase W, it affects the noise margins in a good way. With the trade-off, I need to keep my devices as small as possible so I can fit more of them in a smaller space. Now, okay. How do I explain this? I know the point I want to get to, and it has very little to do with what it says on this slide. Wn over Ln is going to affect V out low. If I make Wn over Ln larger, this half of the voltage transfer curve is going to get closer to 0, which is a good thing. Now, if I change the W over L ratio of the P transistor, that's just going to affect the on resistance of the P channel resistor, which is only going to affect VO high. And it's going to move this VO high closer to VDD. So each transistor has its own effect on the voltage transfer curve. I can make the NMOS bigger, have a bigger W over L, and I get better performance when the output is low. I can make the PMOS transistor bigger to give it better performance when the output is high. That's basically all I was trying to say with that. That's the point I'm trying to get across. You guys are so lucky. For the past year, I haven't been in the lab to explain things to people, and it's been horrible. It sounds like what we want to do here, if we want ideal performance, we make W huge, both WP and WN huge, and I get better performance. The trade-off is I make the W's huge, I make these squares bigger, and I'm going to have less devices that I can sell. The cost per wafer is fixed given the process. It can be these things are expensive. It can be $100,000, and as the processing dimensions go down, it's more. The price keeps going up, but the processing dimensions mean I can squeeze more chips on there, so I've got more die to sell. I've got the same cost depending upon how many squares I break this down. into. If the die, and the die is the little square right here, if each die is smaller, I can put more of them on the wafer. I can get a lower cost per die. Now, another thing that's going on is that when I test the wafer, one of the first things I do is I put a probe card down on here, and I actually make contact with these really sharp needles with the die, and I put power and ground every single chip. And the ones that are I measure no current from, I put they actually physically put big black dots on them. And that's telling me that those are bad, and don't even package them. Don't spend any more money on them. They're already dead. The percentage of chips that don't have a dot on them, that's my yield for the process. If I get a higher percentage of good die, I've got more die I can sell. One of the things that makes you a big hero at Micron or any semiconductor manufacturing plant, any manufacturing plant, is getting the yield up. It's like free product. You've just generated free money for them by making more of those black dot devices useful. Finding ways to do that is a whole other thing. Okay, so when I'm looking at these MOS transistors, this is the top view. It's an N+ region, so N+ diffusions means this is an NMOS device. And I'm looking at it in the top view. This is like looking from Google Earth or Google Maps, where you're looking down at the top view and you can see all the buildings and everything, but you can't see the street. You can't really see what's going on in the street. If I move it over, and if they do this, it takes a saw to do this. They take a saw and run a cut through here and flip it over on its side, you can see the side view of what's going on. So it's just like two different mechanical drawing views, or looking at like a satellite image versus looking at a street view image. You get different information for both of these. If I want to see the storefront, I need to have the side view image. And the side view image, the cross section, contains things like, oh, I can see how deep this N+ diffusion is going. And the different materials have slightly different shades of gray on the black and white, and you just kind of learn how to read that. The poly has a slightly different shade of gray, and the oxide looks a little bit different too. And you can start to distinguish these features and figure out what's going on. By the time we get to lab 4, I'm going to give you a drawing like this, and I'm going to ask you to draw the cross section. That's week 1 of lab 4. We're not going to get there yet. If I want to think about where W over L is on these transistors, the length of this is the drain, or it doesn't matter. The drain and source are interchangeable. They're symmetric right now. But we'll just call this one the drain. We'll call this one the source. This is the gate. The red area is the gate. And to find the size of the transistor, you need the area of the gate. The length is the distance between the drain and the source. So it is this dimension right here, L. Now the width is something that I see students mess up every once in a while. Is this gate is poly, but the only part of this that is actual transistor is the intersection of the drain, the source, the intersection of the active region with the gate. So the width of this only extends up as far as those diffusions go. It's not the whole length, it's not the whole width of that red box. It's only as far as the intersection of poly and active go. On this drawing, the length is going in this direction, and the width would be out somewhere in the 3rd dimension that we can't see. Okay, different information for both of these. We have an electron microscope at NAU in the physics department that can actually look at these cross sections. We don't have the capability yet to saw them ourselves, but we've got people doing it for us. And one of our grad students is looking at cross sections for some of the devices that we're using. It's pretty cool. She's actually was an electrical engineer, and now she's getting her PhD in physics. So. Now, if I want to build an inverter, I need both an NMOS transistor and a PMOS transistor. The NMOS transistor is generally the one with the smaller W. We'll talk about the why of that later. The other thing that tips off that this is the NMOS transistor is the N plus diffusion down here. So remember, the NMOS had N plus diffusions, and you create an N channel in between them. So this is the NMOS, and this is the PMOS. They both have the same length. The length is in this direction, and it's probably the minimum length of a transistor for this device. The width of the NMOS is much smaller than the width of the PMOS, and there's a reason for that. That's WP, this is WN. Typically, kind of a rule of thumb when people are designing these things, people use somewhere between 2.5 and 2. We make the PMOS bigger by that much because the holes in the PMOS, in the P channel, move slower through the material than the electrons do. So in order to make up for that difference in speed, if I make the PMOS transistor bigger, I'm going to get a speed increase by this factor that the width is bigger. So it helps balance out the speed between the PMOS and the NMOS by making the PMOS bigger. Okay, now we're going to go back and review MOSFETs. We won't get this. This is pure review. It's 280 stuff. We want to look at channel formation. We want to look at the structure a little bit, why it's called a field effect transistor, and the ID/VDS characteristics. We'll get to that on Tuesday, some of this. This is a planar MOSFET. This is the way they were designed from the 60s when they first were able to build MOSFETs. MOSFETs, the concept for a MOSFET came from the 1920s because it's simple and people understood how to use it. The problem was they didn't have the material purity to actually make it. That didn't come along until about the 60s. Basically, this is an N-channel device. It's got a P substrate. It's an NMOS. I've got N plus diffusions. One of these is the source and one of these is the drain. It's completely symmetrical. It doesn't matter which I call the source and drain until I put it in the circuit. The drain has generally higher voltages than the source, so VDS is greater than 0. And that will define which one is the drain and which one's the source. The gate's this big area right here overlapping the channel. When I put a voltage between the gate and the source, what I'm going to do is put positive, negative. A positive voltage at the gate with respect to the source. And we'll just say the source is grounded for this example. what happens is I collect positive charge on this plate. It's going to act like a capacitor. It is a capacitor. They call it a MOS capacitor too. And the electric field across that capacitor is going to induce negative charge to collect on the other side of the plate. When I get this region in here where I've got a lot of electrons in the N plus, a lot of electrons in the N plus here, and I've got a lot of electrons in the channel, the semiconductor becomes conducting. And I've turned this transistor on. The material point of view, for the material science point of view, Cedra Smith uses silicon dioxide for the dielectric. Silicon dioxide has an epsilon relative of 3.9. When we go to those smaller sizes, I need a higher dielectric strength to maintain the electric field without punching through with the thinner oxides. The first thing they did about 10 years ago is they went to putting hafnium, nitrided hafnium silicate. A lot of times they just call it hafnium for short. It has a dielectric strength of 20. That was what was mainstream up until about, well, now. To go into the deep nanometer devices, the 3 nanometers, the 5 nanometers, they're starting to use these rare earth oxides that even have a higher dielectric strength. But for understanding the concepts, silicon dioxide is fine, and nobody wants to rewrite Cedra. The L keeps going down. Samsung is in very early production of a 1 nanometer process. 5 nanometers is what they're building down, the production line they're building down in Phoenix now, the new TSMC factory. It keeps getting smaller because for like these computers and processors and memories and things like that, in order to get those die sizes really small, when you have billions of transistors in there, you want to get the minimum length of the transistor as small as you possibly can. And that minimum length is so important, it ends up in the name of the process. The oxide's only 10 angstroms thick, which is only about 10 silicon atoms. So a few defects in there can really blow your devices. It's amazing the precision they do this stuff with. From a circuit designer's perspective, you change the parameters and your circuit stays the same. From the processing engineer's perspective, there's a lot of big changes going on. Okay. Now, this is pretty important here. There's some threshold voltage that I've got to put, that's the body, I'm going to put between the gate, the source, and the body. I have to put a minimum voltage across there in order to form this channel, to turn this transistor on. This is called the threshold voltage. It's pretty important to know. Now notice on these, I've added another little thingy here. This is the source, this is the drain. There's a body tie connection on here. And generally they put the body tie through a P plus diffusion into the substrate. The P plus just makes it a lower resistance contact. And you have to make sure you tie the body down. And I will babble on about that someday when we get to the appropriate time. If VGS, the voltage between here is 0, I don't have any charge collection. There's no channel. I've got I've got reverse bias diodes. You can see here, I've got a P, I've got an N, and the diodes are reverse biased, so there's very little current flowing. There's some leakage current, but for most cases, we just call it 0. As VGS gets bigger, I get more positive charge collecting on this plate, more negative charge collecting on this plate. I get this channel in here where electrons can flow easily because there's electrons here, there's electrons here, there's electrons here. I get a channel where current can flow easily. The transistor is on. Okay. It is a symmetrical device. If I get the gate to source voltage greater than VT, I'm going to form a channel at this end. So having a channel at this end is when VGS is greater than VT. So both of those have VGS greater than VT. This one doesn't. There's no channel. In this case, I've put enough charge on VG relative to VD to form a channel at the other region. So this is VGD is greater than VT. I get a bigger channel in that case. If I go over here, I don't have enough VGD to form a channel at this end. And I certainly don't have enough down here either. And this corresponds to the 3 regions of operation of a transistor. If I have no channel forming, this is called cutoff. Give me a second. VGD. I want VD to be hot. If I have a channel forming at both ends, I'm in triode. And if I have a channel not quite forming at the other end, I'm in saturation. Wow. And I just did that. Now, we want to look at this. I've got 3 voltages that I control. The body is generally tied universally to ground in NMOS transistors. In the lab, when we draw these transistors, we're going to use the 4-terminal devices. You are going to have to manually tie the bodies down. For NMOS, the body always goes to the lowest voltage in the circuit, and that is generally ground. And this is to keep this all these PN junctions back biased. If you forward bias those PN junctions, you get current in places you don't expect, and you get a big mess. Your multiplexer becomes an imager. For the PMOS transistors, we're going to tie the body to the highest voltage in the chip, which is generally VDD, and that will keep those diodes back biased. Remember, PMOS is going to be built in an N well, so the N wells all get tied to VDD, the P substrates get tied to ground. And that's just to keep all the resistors, all the diodes back biased. Now, if the gate voltage goes up, both the 2 things we care about, yeah, I'm right. The 2 things we care about are VGS. We want VGS greater than VT And we may need VGD greater than VT. So if the gate voltage goes up, both VGS and VGD are going to increase, which is going to give me a bigger channel. I'm going to put the word channel up here. You know, I don't crash my computer as much when I talk slower, when I write slower, and I'm talking slower and I'm writing slower because I'm not so rushed this semester. If I decrease the value of VG, I'm going to get a smaller channel. Now, if I increase VS, it really is only going to affect the channel at this end. But if I increase it, VGS goes down, so my channel gets smaller at the source. And if I decrease it, it'll get bigger. The drain voltage, now I'm looking at VGD. If I increase the drain voltage, VGD is going to go down. And that means I'm going to get a smaller channel at the drain. And this will be a bigger channel at the drain. Now, how does the size of the channel that we're creating with these induced voltages affect the resistance? If we go back to physics, this is a material. And this material has some material property based upon the doping, with the impurity concentration and everything it has in it. It has a thing called resistivity. And it's a material property that you can look it up in a table. The actual resistance of this channel, which we want to be low when it's on and high when it's off, is going to be equal to that resistivity that's fixed once I get the material down, times the length of the channel. So if I make this channel longer, the resistance is going to go up. And this is the on resistance. And if I make it wider, if I make it where the current's flowing this way, if I make it wider or I make it thicker, it's going to go down. And the units of resistivity, well, I've got to have ohms on this side. R equals rho L over WD. L, W, and D are all going to be in centimeters because that is what the original solid state physics people thought every transistor would be in lengths of centimeters. And they're not. I've got ohms on this side. I've got the units of resistivity. I've got something in centimeters divided by centimeters squared. And so when I flip all that around and multiply it out, the units of resistivity are ohm centimeters. Kind of weird units, but that's what it is. Okay. And we just did this. Okay. Remember this cartoon. Ricardo Toledo is the one who came up with this. If I think about this inside a transistor, Dan Shavar, he used to do this thing. He was talking about it's MOSFETs are like stepping on a garden hose. When I apply a voltage to the channel, it's like I'm letting my foot off the garden hose so the water can flow. When I take the voltage away, the energy away, my foot drops and I can't have current flowing anymore. So the three stooges of current flow right here. This is the guy, ohm. Basically what he's doing as he pulls, this is reducing the voltage. VGS. This channel is the, oh great. I talked too soon. I'll talk through the slide and then I'll reboot. This volt guy over here is VDS. So if I put a higher VDS through here, I'm going to be able to put more energy in VDS. I don't know, can you see? No, you can't. If I put higher energy in VDS, I'm going to try to squeeze more current through. I could also let more current through by letting up and increasing VGS. I will be back in about 30 seconds. My computer just froze. We are on slide 24, number 13. Okay.